Section 8.2.
Any of those, no, the charts on the test. Oh, yeah. What are those called? Slope fields?
The slope fields? Nah, I didn't put a slope field problem on the test.
Okay.
I originally had a slope field problem, and I also had to find the orthogonal trajectory problems.
It's pretty good.
But then I worked it out, and I thought the test was too long, so I cut those two problems off. I thought so. All right, so section 8.2, we were integrating by parts. And what was integration by parts? When did we use it again? What was it good for? Integrating when you have what? Usually you use it when you have integration and there's multiplication involved. So this was kind of the reverse of the chain rule. And so our rule was the integral of u dv was u times v minus integral v du. And we saw the other day the most challenging part was deciding what the letter u should be. But we had a little rule to help us remember what u should be. What's a little rule for u? Not I hop. I late. So our little rule for picking u, I hop would be cooler if we could make it work, but it was I late. And I stood for inverse, those would be inverse trig or inverse hyperbolic. L was logarithm. A, algebraic. So this was like x squared, x cubed, those sort of things. T, trig, and E, exponential. All right. So, for example, let's say I gave you the integral of x cosine of 4x dx. So here's kind of the thinking that I go through. I first ask myself, is u substitution going to work? U substitution is my favorite way of doing it, and you're shaking your head telling me, no, u substitution will not work. What's wrong with u substitution? You can't get the x dx. So you would let u be the 4x, but you can't get the x dx. If this were a 4x squared in here, it'd be okay. You could use u substitution. All right, so that's the first thing I always look for. Can I use u substitution? The answer is no. The next thing I see is I have multiplication, x times cosine 4x. That's a big indication to me that I should try integration by parts. And seeing as at this point in our life it's the only other option we have, that kind of narrows it down. But in the near future, we're going to have lots more options. So you're going to need to learn to recognize when to use which technique. All right, so in this case, we're going to try integration by parts. And we think u should be x. Because algebraic, which is the x piece, comes before t, which is the trig piece. So that means dv should be everything left, cosine 4x dx. And then this is why we pick u to be x. This is what we really want. When we take the derivative, what's the derivative of x? Just dx. So that piece goes away in a sense. And that's what you really want to have happen. V, on the other hand, we integrate. What's the integral of cosine of 4x? That would be the 1/4, right? So to integrate this one, this is really a u substitution problem. Except I don't want to use u because I already used u. So we would use another letter. No, you use u, you use v. No.
T.
U, V, W, folks. next letter line, U, V, W. So we would have w equals 4x. So dw would be 4 dx. So you'd have to sneak in a 4 and divide by a 1/4. So this becomes 1/4 sine of 4x. All right, so now we use our formula. Our formula says we take u times v. That's x times, does it really matter if I used w or not, by the way? I mean, could you have used p or r or any other letter? I was just being stubborn, that's correct. Any letter will work. Anyway, u times v is x times 1/4 sine 4x minus integral of v, which was 1/4 sine 4x, du, and du happened to be dx. All right, so notice what integration by parts did for us. Basically, it got rid of the multiplication problem, didn't it? Originally, we had x times cosine x. Now we just have a sine x, but we don't have any more multiplication. So that's an improvement. Can you take the antiderivative of 1/4 sine 4x? Yes. And what do you get?
1/4 cosine 4x. Oh, you get cosine 4x. No, you get 1/16.
This 1/4 is going to survive. And then again, you have to do another w substitution. So again, w is going to be 4x, dw is going to be 4dx. You're going to divide by another 4. So you're going to have a 1/16. No, we can use w because it's the same thing again. It didn't change. And then you're right, you're going to have the antiderivative of sine is negative cosine, so you're going to have another minus sign. So it's going to be a plus. So your final answer is going to look like 1/4 x sine 4x plus 1/16 cosine 4x, and then we throw a plus c on the end. Questions on that one?
So should there be a plus? Yeah, and plus C. When we go to evaluate the answers out. Okay.
So your question is, I think, back here when we figured out v, shouldn't we have put a plus c there?
Yeah, kind of. Because I was wondering, when we do that, it comes back in and then we integrate. So I was a little lost.
All right, so the answer is you can put a plus c there if you want, and interesting things happen. You're going to like interesting things because this is exactly your next lab.
Okay.
What happens if you put the plus c in there? Okay? Interesting things happen. And you'll see what happens when you try it in the lab.
Why don't we try it beforehand so we're correct?
Well, I don't want to give away all the exciting answers.
It would be c times x when you integrated it, and which is a variable and some random number multiplied. So technically it's still just a number, but at the same time it's related to that variable.
So what you're saying is it should all work out.
Should, but at the same time it's an interesting proposition.
That's right. And the answer is it does all work out, but it looks weird. So you'll see when you get to the lab.
That's what I was like.
Integral of x squared e to the 5x dx. All right, once again, I check quickly and I see that u substitution doesn't work because u would have to be 5x. Not going to work. I'm not going to get the x squared there. So that tells me now I see multiplication, integration by parts. U should be x squared, which means dv should be e to the 5x dx. And why did you pick u to be x squared? Why didn't you pick u to be e to the 5x? Because your word told you to. Because a comes before e in I late. A is algebraic, e is exponential. And it works out that a comes before e in the alphabet, but no other time. All right, so du is 2x dx, and v would be, what's the antiderivative of e to the 5x? 1/5 e to the 5x, very good. And that's, again, technically a little u substitution problem. That's what you get. All right, so here's our answer. Our answer is u times v, that's x squared, 1/5 e to the 5x, minus the integral of v, which was 1/5 e to the 5x, times du, which is 2x dx. Excellent. We have to do it again.
Is it, oh, this is one we want to do it again.
Right. All right, so I'm just going to rewrite this slightly. I'm going to write this as 1/5 x squared e to the 5x minus, I'm going to take this 2/5 and this 1/5, and I'm going to pull them, and this 2, I mean, and pull them both out. That becomes a 2/5 integral x e to the 5x dx. So notice what happened. In our original integral, we had x squared e to the 5x. In our new integral, we have x e to the 5x. Has it gotten better? It has gotten better. Unfortunately, we still can't integrate it directly, can we? We can't use u substitution still. We still have multiplication there. So what do I have to do? I have to do it again. And that happens sometimes. Sometimes you have to do integration by parts multiple times within a single problem. And I'll show you in a minute the quick way. And you'll be very happy that I show you the quick way. All right, so this time, the second time through, u should be x, and dv should be e to the 5x dx still, correct? du is dx, so that's good. That one's going away. That's what you want to have happen. You want to have one of them go away. V will still be 1/5 e to the 5x. All right, so we have 1/5 x squared e to the 5x minus 2/5 times, I got to take this negative 2/5 and multiply it by everything coming up here. U times V was x times 1/5 e to the 5x minus the integral of V, which was 1/5 e to the 5x, du, which was dx. And now we can finish it off, can't we? Because now this is something we can integrate directly. All right, so it looks like our final answer is 1/5 x squared e to the 5x. I'm going to distribute this minus 2/5 through, so that's minus 2 over 25 x e to the 5x. And then I'm going to have a negative 2/5, and then I'm going to have a negative 1/5. But then when I integrate one more time, what's going to happen? I'm going to get another 1/5, aren't I? When I integrate e to the 5x, I'm going to end up with another 1/5. So I've got a negative 2/5, a negative 1/5, and another positive 1/5. So what's 2/5 times 1/5 times 1/5? 2 over 125. And it's a plus, isn't it? Because it's a minus and a minus. Plus 2 over 125 e to the 5x plus c.
It's 5 times 5 times 5.
Because it's 5 times 5 times 5. Yep. Questions on that one?
So on the lab, are we going to do one where it's what happens at the end? See, there's like several steps?
No. So on the lab, you're gonna it'll be one like this one. One like this one was just a one-step one, and you'll put the plus c in right here, and you'll see what happens. So you'll do it without the plus c, the way we just did it in class. Then you do it with the plus c, and see how the answers compare, and see if the answers are the same, see if they're different, see what's different about them. Okay.
So is the exponent on the x, is that going to determine how many times you do?
Absolutely. That was my very next question. So notice when we had just an x here, we had to do integration by parts once. When we had an x squared, we had to do integration by parts twice. If I gave you an x to the third, you'd have to do integration by parts 3 times, and it would get pretty long and involved, wouldn't it? What if I gave you an x to the 5th? Yeah, you'd quit on me, wouldn't you? You'd say, crap, I'm not doing that. You're nuts. You weren't sure if that was the right answer? All right, so here's the shortcut technique. This is called the tabular method. We'll do almost the same problem. Let's do it with we'll just do x cubed. Integral of x cubed e to the 5x dx. We could do it directly. We know we'd have to do it 3 times, and it would work out. Kind of a pain in the neck, but not so awful. What you do is you pick your thing to be u. What's u going to be? X cubed. And you go down here and you take derivatives. And you keep taking derivatives till something happens. When do you stop? When it's disappeared. So what's the derivative? 3x squared. What's the next derivative? 6x. 6, 0. So that tells you to stop. Okay. Over here you write your dv. dv is e to the 5x. You integrate. What's the integral of e to the 5x? 1/5 e to the 5x. You integrate again. 1/25 e to the 5x. You integrate again. 1 over 125 e to the 5x. And you integrate one more time. 1 over 625 e to the 5x. And how do you know to stop there? Because that's where the other one stopped. You stop at the same place. All right, and then you come over here to the left-hand side and you write plus, minus, plus, minus. Why plus, minus, plus, minus? Oh, you know what? I started in the wrong spot. The plus should have gone where the u is. Plus, minus, plus, minus, plus. You always start at the top. Start where the u is. Why do the signs change? Why plus, minus, plus, minus?
Because
Correct. Look what happened with this one. When we did it twice, the first one had a plus, but the second one had a minus because it was minus integral v du. You can see that up there. There it is. Minus integral v du. But the third one, the last one, ended up with a plus because we had the minus from the first integration by parts, and then we had another minus from the second integration by parts, so that one ended up back to plus, didn't it? Okay, so here's your answer. Go ahead.
when doing the derivative or gain derivative, is that truncate the pluses and minuses in the front, or do they just have the minus here and then the derivative this one's minus?
The pluses and minuses are completely independent from your derivatives. So if these have pluses and minuses in them, we'll take care of that in just a second. All right, so here's your answer. What you do is you multiply. So you multiply across, so you get a plus, you go to the u, and then you go down one level there. Because that's u times v, right? That's how we start. U times v. So there's your first term. Your first term is going to be x cubed, 1/5 e to the 5x. Then you go to the next row. The next row starts with a minus. So you're going to have minus 3x squared. And then you go down one spot there. So it's 1/25 e to the 5x. And you just keep going. So the next one is plus 6x 1 over 125 e to the 5x minus 6 times 1 over 625 e to the 5x. And then you stop because the next one would have a 0 in it. So, plus c. So there it is. There's the tabular method. It is nice.
Especially with like harder derivatives and integrals where you're like, so there are, I'm guessing the ones with like integrals where you have to do substitution like every single time and then like hyperbolics and stuff like that.
So, my personal method is anytime I have to do integration by parts more than once, I use the tabular method. Even if I only have to do integration by parts twice, I think the tabular method is easier. So if I had this problem, if somebody gave me the integral of 6x squared sine of 4x dx. I would look at that and I would recognize right away that I'm going to have to use integration by parts twice because I see that 6x squared. So personally, I would use the tabular method. So I would start with u equals 6x squared, and dv is sine of 4x dx. And that one gets the plus. I take the derivative. The derivative of 6x squared is 12x. I take the second derivative. I get 12. The next one is 0. I get to stop. Over here I integrate. The integral of sine 4x. 1/4 cosine 4x. Integrate again. Negative 1/16. Shouldn't the first one have been negative?
Yeah.
Yes, it should have been. The derivative of sine is cosine. The integral of sine is negative cosine. So we integrate again. We get negative 1/16 sine 4x. We integrate one more time. We get 1/64 cosine 4x. Plus, minus, plus, minus.
Do you have a negative in the 1/4? Why would the second one be negative too?
Because the integral of cosine is positive sine. It doesn't add another negative till later. Till you do integral of sine again. The integral of sine gives you another minus, and that one becomes the plus. All right, so here's the answer. The answer is, now notice I've got a plus here in my original thing, but when I multiply through, I've got a 6x squared times a negative 1/4. So even though this is a plus times a minus is still a minus. So the first term is still minus 6x squared times 1/4 cosine 4x. And then the next one has a minus here, but it's got a minus there, so that one becomes a plus 12x 1/16 sine 4x. And then this one's a plus because it's plus all the way across. So that one's plus 12/64 cosine 4x plus c. Okay, so that's my opinion. Anytime I see I'm going to have to integrate by parts more than once, I jump immediately to the tabular method. Do you have to? No, if you don't want to. If you like writing out u and v each time, that's fine. That's your choice. All right, now we got the trick problems. Integral of ln x dx. This one, when you look at it, you probably would not think you should use integration by parts. Why would you might not think that? Yeah, but there's no multiplication, right? And that's what usually triggers you to use integration by parts, is when you see multiplication. So that's why this is sort of a trick problem. But it turns out integration by parts works really well here. And Jesse said exactly the right thing. U should be ln x. And everything left, we do know the derivative of ln. So du is 1/x dx. And v is just x, correct? U times v, that's ln x times x, minus integral of v, which is x, times du, which is 1/x dx. So, yeah, these reduce. It's the integral of dx again. So our final answer is plus c. X ln x minus x plus c. So that one's kind of a trick question in the sense that you would look at it and you wouldn't necessarily think right away integration by parts. So if you were to take the derivative of this, you can go home and check it. Take the derivative of x ln x minus x. You should end up with ln x. Try it, see if it works. I promise it does. He's checking it anyway. He doesn't believe me. The same sort of trick would work. I'm not going to do it. But if I had just like the integral of arc sine dx, the same sort of trick would work. You would let u equal arc sine, because it's the only thing there. And then dv would be dx. So that's another one you'll see in your book worked out. That's another one that's a lot like this. All right, the other kind of tricky ones that you run into.
So there is that one integral you said it does not have any solution whatsoever. And confirm that should have it's impossible to solve.
Correct.
Is that shown by using integration of parts?
No. No. I honestly don't know how that was proven that it cannot be done.
But your teacher just said don't try.
Well, my teacher said don't try it, and I believe my teachers. How about the integral of e to the 2x cosine x dx? U should be a cosine x because t comes before e in ILATE. Trig comes before exponential. So u is cosine x, which makes dv e to the 2x dx.
I do have one question. How do we know how many steps it's going to take if we don't have an algebraic exponent?
Excellent question. You don't. You don't know how many steps it's going to take. If you have an x squared, you know it's going to take 2. If you have an x to the 10th, you know it's going to take 10. If you don't have either of those, you start going until something good happens.
Can we use the tabular method on like cosine squared x?
No, for cosine squared x, you would have to do something else.
Okay.
And we'll get to that. That might be the very next section, powers of trig. Something else. All right. du, derivative of sine is negative, derivative of cosine is negative sine. And the integral of e to the 2x is 1/2 e to the 2x. We'll see. But it works out. All right, so we're going to have u times v. U was cosine x, and v was 1/2 e to the 2x. Minus integral of v, 1/2 e to the 2x, times du, which was minus sine x dx. No, because this one was derivative. The derivative of sine is cosine. And the derivative of cosine is negative sine. So that one should be a negative there because we did derivative, not integral.
Stay in this forever.
Stay in this forever? What do you mean?
Because your u is always going to be a trig
It's
function.
always going to be e to the 2x and the trig.
Yeah.
So what you're telling me is we started with an e and a cosine, and now we have an e and a sine. Did it get any better? No, but on the other hand, did it get any worse? No. So we keep plowing forward and hope something good happens. I'm not kidding. We plow forward. All right, so I'm going to rewrite this as, I wasn't kidding you, 1/2 e to the 2x cosine x plus 1/2 integral e to the 2x sine x dx. So I just cleaned things up a little bit there. In my integral, I pulled out the negative 1/2, and that's what I have. And you're right. What you've recognized already is this thing's just going to cycle around and around and around. But there's going to be a way to fix it in the end. All right? So we're going to do integration by parts again. Whole thing again. So this time, second time, u is sine x, and dv is everything left, which is e to the 2x dx. So du is cosine x dx, and v is still 1/2 e to the 2x.
And what occurs 1/2 or just half? Or just e to
1/2 e to the 2x, when you integrate that.
the 2x? Oh, right.
Again, that's a little u substitution problem. U is 2x. All right, so we're getting there. I know it doesn't look like we're getting anywhere, but we are. 1/2 e to the 2x cosine x plus 1/2 times u times v. That's a sine x, and a 1/2 e to the 2x minus the integral of v, which is 1/2 e to the 2x, du, which was cosine x dx.
Now, because the fraction we're finding gets exponentially smaller, does something go to 0 automatically?
No, that's an interesting way to look at it. You're right. The exponent's going to keep getting small. The power on bottom is going to keep getting bigger. So if you were to keep going, this fraction would continue to get smaller. It would converge to 0. Yeah, but that's not what we're going to do. We're almost there. We got like 2 more steps. 2 more easy steps, though. All right. So easy step number 1. I'm just going to pull my powers out, pull my 1/2s out, and clean stuff up. 1/2 e to the 2x cosine x plus 1/4 e to the 2x sine x minus 1/4 e to the 2 integral e to the 2x cosine x dx. Correct?
Yes.
So what you notice happens at this point, you notice that the integral has cycled around on itself, hasn't it? We're right back to where we started with. So what we're going to do is we're going to take this right here. It would be better if I wrote it this way. I'm just going to rewrite the whole thing down again. Integral e to the 2x cosine x dx equals 1/2 e to the 2x cosine x plus 1/4 e to the 2x sine x minus 1/4 integral e to the 2x cosine x dx. So we've cycled around on ourselves. So what I'm going to do now is I'm going to take this thing right here that I cycled around to, and I'm going to add it to both sides of the equation. So I'm going to add 1/4 integral e to the 2x cosine x dx. But if I add it on the right-hand side, I have to add it on the left-hand side. Plus 1/4 integral e to the 2x cosine x dx. So what happens on the right-hand side? Those cancel out. They add up to 0. What happens on the left-hand side? Yeah, I have one thing plus a quarter thing. That's 5/4 thing, right? Where this thing happens to be integral. So we have 5/4 the integral of e to the 2x cosine x dx equals 1/2 e to the 2x cosine x plus 1/4 e to the 2x sine x. And finally, to get this integral thing all by itself, which is what I wanted from the beginning, multiply the whole thing by 4/5. So final answer. Got to sneak it in here. I got just enough room. Integral of e to the 2x cosine x dx equals, when I multiply by 4/5, I'm going to have 2/5 e to the 2x cosine x plus 1/5 e to the 2x sine x plus c.
I was going to say, where did you plus c come in?
Right there, I sneak it in at the end.
You just
Plus
want
c.
to say, oh, by the way, it's there.
And it's plus c.
So I didn't transfer sides or anything? Or was it there all?
It was there all along. We just chose to write it in the last step. All right, so there's the hard ones. Sometimes when you have an integration by parts problem, like we did here, it cycles around on itself. So when it cycles around on itself, once you see that it cycles around, whatever you get for the repeat thing, you're going to add it to both sides of your equation and then just divide by the number that turns out in front.
So how would this look in the tabular form when you do it? Would it be easy to recognize in the tabular form and then set it up? I think it would be easier to do it this way.
I think so too for this one. Let's try that on Friday. Let's try the same problem on Friday. We'll try it in the tabular form. The problem you're going to have with the tabular form is you're going to let u equal cosine x, and you're going to start taking derivatives, and when's it going to go away? When's it going to be 0? Never. But you might notice that
It's wrong to itself.
once it cycles around to itself, maybe that's the time to stop.
Because then technically you should just
Yeah.
continue in the loop.
Should continue to look. I don't think I've ever seen a problem like this done in the tabular method. I've always seen them just worked out, do the integration by parts twice, add to both sides, and divide.
How could somebody did it